We have Aurel computing groups of Hecke characters.
Okay, thank you. So, well, first, thanks to the organizers for putting together this new edition of ANTS, and I hope you will all enjoy this week. I will, for sure. So this is joint work with Pascal Molin, who is, right there, about computation of groups of Hecke characters. And so, okay, I'm going to tell you a bit about what Hecke characters are, either introduction, depending on your background, or a reminder. Then I'm going to tell you a bit about the algorithms that you use and what they actually do. And a bunch of interesting examples. I mean, it's a selection. There's a bit more in the paper if you would like to see some more things. Okay, so Hecke characters. So first, let me give you a few examples of Hecke characters that you may be familiar with, and then I'll give you the actual general case. Okay, so over the whole talk, we'll have a number field called F with ring of integers ZF. And from that, you can pick an integral ideal of ZF, and we call that a modulus. I'm going to omit the possible infinite part that you can put in a modulus for simplicity. And from that, you can construct Ray class groups, namely generalizations of the class group. You just take ideals co-prime to M, fractional ideals, modulo the ones that are principal, generated by an element congruent to 1 mod M. This forms a finite group. If M is the trivial ideal, this is just the class group. And therefore, you can consider characters of this finite group. And these are precisely the finite order Hecke characters. So the more general Hecke characters that we are going to see later are generalizations of these, except that they don't have to have finite order. So a bunch of properties that these kind of characters have. So they have a various modulus. So you have maps between these groups, and therefore a given character could come from some lower modulus instead of the one that you started with. And the smallest one for a given character is called its conductor. So that's one of the invariants attached to such a chi. You can evaluate characters at ideals that are co-prime to the modulus, and that will give you values that are roots of unity, complex numbers, but here roots of unity. And also you have a map from the units of this finite ring ZF modulo M to the class group simply by sending an element that is co-prime to M to the ideal that it generates. And you can see that this map is well defined, and therefore a given chi, you can restrict it to that group, and you get a character of this finite group. And that's one of the, okay, it may seem a bit arbitrary maybe to do that here, but it's going to have a more natural incarnation a bit later. And okay, this is maybe the more, I don't know, we could say automorphic perspective on Hecke characters, but there's one of the things that are interesting about them is that they correspond to Galois characters of finite Galois extensions of F by class field theory. So you can, I mean, you have these characters seen intrinsically in terms of F, but they also correspond to characters of finite Galois extensions. Okay, so in terms of computation, this is, I mean, Ray class groups are something that we've known how to compute for some time, and therefore this type of Hecke characters, we also, I mean, they're just characters of these finite abelian groups. So we've had methods to compute these Hecke characters for a long time too. Okay, so let's look at more general cases. First, I'm not going to give the precise definition, but there's one more general case that people encounter maybe more often than the most general case, which is algebraic Hecke characters. And the reason why people typically encounter them is that they play a role in CM theory, right? The theory of CM abelian varieties. So algebraic Hecke characters also have properties similar to the finite order ones. They have a conductor also, that's also an ideal of the field. They have an infinity type and that's data that's just the data of an integer for each complex embedding of your field. So a bunch of integers. They also have evaluations at ideals co-prime to M, but now they don't need to have finite order, but they are algebraic values, algebraic numbers. And well, that's one way of interpreting the word algebraic in algebraic Hecke characters. They still have a restriction to these kind of groups as before. And now they still have a relation to Galois theory, but in a slightly more complicated way than the finite order ones. They don't correspond to characters of the Galois group with complex values. They correspond, I mean, they have for all p's, in fact, attached Galois characters with p-adic values. Okay. Right, so that's for the case of algebraic Hecke characters. And now let me get to the actual general. Okay, so I wanted to say, again, from a computational point of view, there's been work of Mark Watkins about computing with these type of characters specifically. And well, okay, even with a restriction on the base field, but that doesn't matter too much. Okay, so now I'm going to introduce you to the actual general case of Hecke characters, which is the main focus of our work. Okay, so what are general Hecke characters? Well, they are characters on the group of idèle classes. So what are idèles? This is this restricted product of units of the completions of the various of f at various places. So this is either R or C corresponding to real and complex embeddings of the field, which I will denote sigma later, or p-adic completions at various prime ideals of the field, which I will denote frac p later. And if you don't know what this restricted product is, you shouldn't care too much about it. Just think about a product. It's okay. And so what is a Hecke quasi-character first? It's a multiplicative and continuous map on this quotient group, the idèles modulo the units of f, non-zero elements of f. Okay, we'll unravel this definition a bit to make it more concrete in a minute. So, but first, let me say what an actual Hecke character is. It's a Hecke quasi-character such that the values have absolute value 1. It's convenient to have both types. I mean, the terminology is maybe a bit awkward, but that's what it means. Quasi-character is arbitrary complex values, and actual character, it's absolute value 1. Let me give you our first example of a Hecke character, actually. You can take the following map on this idèle group, namely take the product over all these of the normalized absolute value of the component at V of the element of this product. This is called the norm, and the product formula tells you that it vanishes on F star. And in particular, it's an example of such a quasi-character. It's fairly easy to see that it's actually not a Hecke character. It doesn't take values of absolute value 1. In fact, because the values are positive reals, if it had absolute value 1 always, then it would be identically 1. Okay, maybe questions on this, because this is the main definition of the talk. So any questions? Yeah. Okay, so let's unravel a bit more of the properties of these characters that will make them look like the previous ones that we've seen. Okay, so first, one basic decomposition of the group of Hecke quasi-characters. You can always decompose them as some actual Hecke characters, so values of absolute value 1, that vanish on the diagonal reals embedded in all the real and complex completions of F, times some complex power of the norm. Okay, so that's a way of getting rid of all the powers of the norm. And then you don't have to care about quasi-characters anymore. You just have regular characters, and they have this extra property of vanishing on this copy of our positive reals. The reason you might want to do that is that once you get rid of these complex powers of the norm, which form a continuous family parameterized by complex numbers, you actually get a discrete group. So you could enumerate them one by one. Okay, so that's probably good for computation. If we have something discrete, we'll be able to describe them by a finite amount of information. Okay, and some basic property of this decomposition: you get a character if and only if the power of the norm is purely imaginary. Okay. Right. So now we are in this discrete setting. We want to refine a bit more this decomposition so we can get actual nice groups that we can compute. And the way we're going to do that is by introducing modulus that will be analogous to the modulus that we had for finite order characters. So we'll say that a Hecke quasi-character has modulus M, so M is again an ideal of ZF. If it vanishes on this specific subgroup of idèles, so that things congruent to one mod the right power of the primes dividing M, and elsewhere just the whole units of the p-adic completion of F. So one basic, yes.
You should explain what vanish.
Vanish, takes value 1 on this. Sorry, yes, that's vanish. Yeah, okay, not 0. Yes, thank you. Okay. So I often think logarithmically of my characters, but yeah, okay, thank you. So again, so every Hecke quasi-character has a modulus, so they all factor through one of these, they all vanish on one of these groups. So you get a filtration on the whole group of Hecke quasi-characters. And for each quasi-character, there is a smallest possible modulus, which again we call the conductor. And that's one of the basic invariants of our characters. And therefore, so now that we've introduced conductors, we can form this quotient. Again, the first quotient by F star is just definition of quasi-characters. We assume that we have vanishing on this copy of the positive reals just to get something discrete. And now we also add this extra vanishing. And the point is that once we take this quotient, the characters of that form a finitely generated abelian group. So we're going to be able to put that in a computer, like we're going to be able to compute a basis. And that's what our algorithms will do. Okay, so I'm giving that, and then I'm giving that a name that's the idèle class groups that we'll actually consider. Okay, so we have a conductor now. What else can we do with these Hecke characters? Well, recall again that this idèle group was essentially a product. Because of that, you can take one of your Hecke characters and restrict it to one of these components, and you get a local component of your character, which is just going to be a character of this local field, either p-adic fields or real or complex numbers. And from this, you can get several things. Well, in particular, if you look at real and complex places, you will get a character of R star or C star, and these have a very simple shape. They're all of this form. The value at z is just some integer power of z over absolute value z. For the real field, this is just the sign of z, and so you can raise it to the power of 0, 1, and then, k is just defined mod 2, and then absolute value to some imaginary power. So there's just two parameters, one integer and one real number at every real and complex place. Yeah, so that's one thing that you get. You can evaluate at a prime ideal that doesn't divide the modulus. You can simply take the restriction the local component at the prime P and evaluate at a uniformizer at P. Okay, and if you don't divide the modulus, well, because your character takes values 1 on this, it's actually well defined, and you call that chi of P. That's one evaluation, and you can extend it multiplicatively to ideals that are co-prime to M. Actually, it also makes sense to do exactly this at the primes that divide M, except that now the value you get depends on the choice of uniformizer. But it's actually a mild restriction. It's actually okay to evaluate also as primes dividing the modulus. And then again, you get restrictions to these kind of groups. ZF modulo pairs of primes dividing M, simply by looking again at the local components. So this is the way you recover the same kind of character of ZF mod M that you had before. Okay, so that's the other invariants and values attached to a character that you get. And putting all of these together, you can form the L function of your Hecke character. That's one of the main interests of Hecke characters, just by writing this Euler product that puts together all the values of chi at the prime ideals. And then using the conductor and the infinity type, you can form a completed L function. And well, there's a simple recipe to do that. And well, the value, this, the function that you get here extends to the whole complex plane as a neuromorphic function and satisfies a functional equation of that form. That's one of the, so that's a theorem of Hecke, who gave his name to these characters, and that's one of the main interests of Hecke characters. Okay, now I will start talking about algorithms. Are there questions so far in the audience or online? We're good so far? Okay. Okay, let's talk about algorithms. So first, I told you that the main group that we would like to compute is the group of characters of this quotient with fixed modulus, because that's a situation where we get finitely generated abelian groups. So we can talk about an actual finite basis of this group, and we may want to compute that. So the way we do this is in the following form. For a fixed modulus, there is a set of two dual logarithm maps of the following form. There are two integers, ln n, and the lattice in z to the l times r to the n, which is explicitly described in terms of the class group, units, and S units of the field, such that, and an explicit logarithm map from this idèle class group that may seem somewhat complicated, but just becomes a quotient of this form, just this simple group modulo a lattice, and a dual map from the characters to the dual lattice of this lambda, modulo z to the n. So the dual lattice of lambda, this is just another lattice, so it has a basis. It's just, as a group, it's just z to some, to the n plus l, and so this is a finitely generated abelian group that we can represent and compute with very easily. And so this map we will be able to compute only approximately, because there are real values there that actually typically take transcendental values. There will be like logs of algebraic numbers, things like this in there. But the point is that we can compute a basis of this lattice and evaluations of this log map L at any given precision in polynomial time from the units, discrete logs in class group, and discrete logs in these finite rings that appeared before. Okay, and sorry, there's something very important that I actually forgot to write here, and this satisfies the property that evaluating a character at an element here is the same as taking the dot product between the value of this log map and the dual log map and taking exponential 2i pi of that. I'm very sorry. Okay, maybe I should even write it on the board to have a job.
The other box.
The other box?
Algebra box.
Oh, sorry. Let me actually write this. So, okay, so in terms of complexity, the whole problem is basically reduced to these computations of class groups and discrete logs, which are not so easy, but we know how to do them. That's where the whole difficulty actually lies. Okay, so that's for general Hecke characters. Any questions about this? Yes.
When you say polynomial time, how are you measuring the input? What is the size of it?
Okay, so I say polynomial. Okay, I should repeat the question. The question is, what do I mean when I say polynomial time? So the input, I mean, the data of the units, the class group and its generators, generators of this is all part of the input. And there's also the precision that is part of the input. Does that answer your question?
But don't you also need information about the character?
Okay, yes. So then, well, okay, when you, okay, so there's two things. There's computing this lambda and this group. So then there's no actual character. So then I have the whole input. And otherwise, the character is given by its coordinates on the basis of lambda dual, just a bunch of coordinates. Yeah, I guess you'll see an example when I show you the implementation of how the input is actually given. Other questions? No. Okay, so one of the other groups of interest are the subgroup of algebraic Hecke characters that I mentioned. So I didn't give you the definition earlier, but the actual definition is that the character is algebraic. I mean, a quasi-character is algebraic if its infinity type is of the form z goes to z to some integer power, z bar to some other integer power. So it's a rational fraction in z and z bar. This actually implies that it takes algebraic values. And we would like to compute the group of such characters. And this is closely related to CM fields. So CM field is a purely imaginary quadratic extension of a totally real field. And it turns out that a number field f either doesn't contain a CM field at all, or it has a maximal one. And there's a theorem of Artin and Weil that tells you that basically, if you know the maximal CM subfield, then you know the group of algebraic quasi-characters. Okay, the word algebraic is missing from this sentence, sorry. So the whole difficulty is reduced to computing this maximal CM subfield. So a priori, you may have to go through all the subfields of F, of which there might be more than polynomially many, or do some Galois theory of F, but we also don't know how to do that in polynomial time. So one of the things that we've done here is we've worked out a polynomial time algorithm that, given F, determines whether it has a CM subfield, and if so, computes the maximal CM subfield. And the whole point is to reduce to some linear equation. Basically, you can write this vector subspace, I mean Q vector subspace of F, defined by sigma of x equals plus or minus sigma bar of x for all complex embeddings. This is, note that this is linear equation in F and Q linear. And we prove that this completely characterizes the existence of a CM subfield and the maximal CM subfield. And now this looks like it could be a bunch of transcendental equations. I mean, typically the sigma and sigma bar, you get them from approximations, but you can actually do the computation of this thing in finite and small degree extensions of F. So you can get a polynomial time algorithm to compute this by using this property. And so from FCM, it's easy to get the group of algebraic characters. And that's what we also do. Okay, let me give you a bunch of examples of what we can do, I mean, of our implementation and what we can do with it. So it's a Pari GP implementation, it's on the master branch, and it will be available in the next release. The interface might change a bit, but this will tell you, I mean, basically how it works. So this just computes the class group and units of this number field. I should say that here it's computing only under GRH, but you can also remove GRH if you want. And then you can initialize here the group of Hecke characters, and I'm taking modulus 1. Okay. The answer is some structure containing some data, and you can ask for the structure with .sig, and the answer will be a vector of this form, telling you too that the group is isomorphic to Z mod 2. There's 2 zeros, meaning Z and times Z, and then there's this placeholder that is an approximate 0, meaning that I'm representing the power of the norm, the complex power of the norm that you get in the group of quasi-characters. And then you represent a character by just its coordinates on that basis. I mean, there's one character corresponding to each of these components. And you can, for instance, ask for the local components of this. Here, the local components, it says 2 and this approximate value, meaning that the local character at the second, well, here at the complex embedding of this field, this is a field with one real embedding and one pair of complex embeddings, is the map Z goes to Z mod, Z over absolute value Z squared times absolute value Z to this power. You can also evaluate your character at prime ideals, or in fact general ideals. And there's a there are built-in functionalities for L functions in Pari GP, and you can just plug in these Hecke characters into this L function package and get, for instance, values of the L function. How am I doing on time? When I don't know when I started actually.
I don't either.
Couple minutes.
Couple minutes.
Okay. Maybe I'll skip some examples, but maybe okay. This one is actually pictures. So one nice thing that you can do with these Hecke characters is that because there are functions on this idèle class group, so this idèle class group may seem a bit abstract, but once you have functions on them, they actually give you coordinates on these idèle class groups. So you can take elements of these idèle class groups and plot the values of the characters. And that gives you a way of just visualizing these idèle class groups. So that's what I'm doing here. I'm taking powers of a given prime and evaluating the basis of the Hecke characters at those, and you get successive values. And well, as you expect, the powers of these primes, they will follow geodesic in this group. Okay, there are two components here because remember, this example where we had a class group isomorphic to Z mod 2Z. So this is we plot on the right or left depending on the value of the finite order character, and the other and the values of the other characters are the x coordinate and the y coordinates. And if you plot values of primes sorted by norm, then as is well known, you'll get equidistribution in the idèle class group. You get points everywhere like this. Okay, one other example with CM varieties. So you can consider Shimura's theory of CM abelian varieties, or you could think about other varieties if you want. And Shimura tells you that if you have an abelian variety that has CM by a CM field, then its L function can be expressed in terms of L functions of Hecke characters, algebraic Hecke characters. And so this is what happens for this example of a genus 3 curve. The theorem tells you that its L function is actually equal to the L function of a single Hecke character, and you can determine its infinity type in a conductor bound that would give you a finite number of candidates for the Hecke character. And then from the coefficients of the L function, you can eliminate all but one candidate and work out which Hecke character this is. We don't actually know how to do that efficiently in general at this point. The point being that typically from this equation, you get the value of sums of values of the characters instead of just the value of the character at certain points. Okay, here are the values of the character that you get. Okay, I don't know too much what the values are. Another interesting thing about Hecke characters are the gamma shifts of their functional equation. For general L functions, you have gamma shifts like this. You have a gamma product. Oh, this would be a gamma C, sorry. That are expected to satisfy some proper restrictions about the real parts of the shifts. And they're automatically satisfied by Hecke characters. But what's interesting is that instead of all gamma shifts that you get from Hecke characters are dense in the family of all the ones that are conjectured to be all the possible ones. And the proof is even effective. So for instance, you can construct, okay, I'll skip this, but you can construct a character that has gamma shifts approximating arbitrary values like pi and e, whatever. And the last example I want to mention is interesting types of characters. I talked about algebraic characters, and up to finite index, this is essentially the same as having the phi parameters of the infinity type being 0. And a natural question is it possible to have partially algebraic Hecke characters? I mean, characters have some of the phi's that are 0, but not all of them. What we proved is that from a quadratic extension of fields, you can build characters that are partially algebraic in this way. And this is the analog of the fact that actual algebraic characters come from CM fields. Except that in this case, we don't know whether this is the only way to construct partially algebraic Hecke characters. And the problem is that in the algebraic case, because of the algebraic values that you get, you can use Galois theory to prove that this is all you get. And here, if some of the phi's are 0 and not the other ones, the values of the characters are not algebraic. So there are some transcendence problems, and we don't know how to prove that this is the only way you can construct partially algebraic characters. Quick ad for an upcoming paper with Alex Bartel, where these type of characters, I mean, this question didn't come out of nowhere. These type of characters actually appeared in the work that we did on Viniras's isospectral manifolds. The point being that this condition is precisely the one that you need for the automorphic induction of the character to Jacques-Langlands transfer to a certain quaternion algebra. Okay, but the details don't matter too much. Okay, that's just an example. Let me skip it because we're over time. Thank you.